Welcome to video 1 for acids and base chemistry. On this first video we're going to review some definitions that we've covered previously and talk about this acid conjugate base and base conjugate acid pairs. Again, we've already covered this topic, so we're just going to be a review. Okay, so some definitions. So we have to define what an acid is, and the first definition we're coming across is the Arrhenius definition. So Arrhenius says that an acid is a substance that when you dissolve it in water it gives H plus ions or hydrogen ion concentrations. So something that would do this would be something like HCl, right, as a H plus when it dissolves in water to give H plus ions. Base is a substance when it dissolves in water increases the OH minus concentration. So something like sodium hydroxide would be an example of a base. We increase the hydroxide ion concentration when it dissolves in water. The other definition that kind of broadens what a base is the Bronsted-Lowry definition. So an acid is still something that donates a proton. It has to have that H plus to come off. Again, HCl is still considered a Bronsted-Lowry acid. But a base is now a proton acceptor. So hydroxide can accept a proton to become water, but other things can also accept protons. If we have that lone pair, if we look at the structure of ammonia, we have that lone pair of electrons on that nitrogen, and it can react with an H plus to accept it to give us ammonium ion. So in this case, the ammonia is the Bronsted-Lowry base. Okay, if it can do either, if it can be either an acid or a base, we call it amphiprotic. So there are 3 examples listed here of amphiprotic compounds. So if it's going to react as an acid, what it's going to do is it's going to give its H plus up, and it'll go to the acid ion plus carbonate ion. Again, this is going to be an equilibrium. We'll talk more about that later. But if it's going to act as a base, it's going to react with H plus to give H2CO3. And again, this is also an equilibrium. And again, this would happen with the hydrogen phosphate ion as well. We have an equilibrium to give H plus PO4 triple minus, or it can react with H plus to give H2 PO4 minus. Water is interesting too because it could be an acid or a base, and if it breaks up it gives H plus OH minus, and it can react with acid to give the hydronium ion H3O plus. Okay, so what's really going on? We talked about this Bronsted-Lowry definition, the ability of something to accept an H plus, a base, and in this case it's going to be water is going to be our base, and HCl is going to be our acid. And we rely on that lone pair. Remember, water is a bench structure. It has 2 lone pairs of electrons. That one lone pair of electrons is going to attack the H plus to give the hydronium ion, as well as the Cl minus. We could look at these. What the result of that is we are going to get a conjugate base from the acid. So our HCl is going to give the conjugate base, which is Cl minus, and it's not much of a base, and we'll talk about that in a future video, and the hydronium ion, which is going to be the conjugate acid. So again, this conjugate means that they're joined together. So we could see here in this nitrous acid example, it reacts with water, which is a base in this case, to give the conjugate base. So we see the acid, that H plus is removed to give the conjugate base, the nitrite NO2 minus ion. The base is what takes that, according to the Bronsted-Lowry definition. So the water is taking that H plus, it's acting as a base, and it becomes the conjugate acid, hydronium ion.